Hello dear students, a very warm welcome to you all to the Power Hour for NEET 2025, and today we will be starting our sessions with the chemistry, and the topic is structure of atom. So it is a very important topic. Dear students, they are asking questions from this topic. Every year they are asking, and it is a very basic topic which is related to there are chapters which will be coming after this. So very interesting topic. Let us start. So we will be covering all these subsections over here. You can see we will be having discovery of subatomic particles, atomic models, application of Rutherford's alpha scattering experiment, and the photoelectric effect. So let us continue and have one by one our subtopic. First subtopic is discovery of subatomic particles. So dear students, it is a very interesting discovery which happened. The J.J. Thomson was responsible for the discovery of electron. He carried out a cathode ray experiment, as you can see over here. So this is our discharge tube. Discharge tube over here. And what he did, he, with the help of a vacuum pump, lowered the pressure inside. See, dear students, we have to get the ions over here. So we have to carry out ionization, and for that we will be having very less quantity of gas. Suppose we are having hydrogen gas over here, it will be ionized H2 giving 2H plus 2 electrons. So these 2 electrons, these are behaving as cathode rays. And what he observed over here was this cathode rays, which we are calling it as cathode rays because they are moving from cathode to anode. They are moving with very high velocity from cathode to anode. He named them as cathode rays. Then after that, he had a pedal over here. He saw that these cathode rays are having collision with this pedal, and this pedal is getting rotated. He also had positive plate and negative plate attached over here. And he saw that there was deviation towards the positive plate. That means they are negatively charged. So many observations J.J. Thomson did, that you can see over here. Every observation we are having that. First observation, as I told you, that the pedal got rotated. That means these cathode rays possess mass. The second observation, that they were deviated towards the positive plate. That means they are having negative charge. So over here you can see we are having this ionization of the gas H2. One more interesting thing he did, that he changed the gas. Suppose in case of this H2 we take D2, where the D is deuterium, you will get 2D plus 2 electrons. So over here also we are getting this electrons only as a cathode rays. Cathode rays are not changing over here. This is a very important point. After changing the gas also, we are getting cathode rays as electrons only. Before this we took the hydrogen gas and we got cathode rays as electron, and now also we get cathode rays as electron. So it's a very important point over here, that the E by M ratio, that the charge by mass ratio we are getting over here is 1.76 into 10 to the power 11 Coulomb kg inverse for all the gases, irrespective of the gas. Irrespective of the gas used, we are getting the same value of charge by mass, E by M, which we call it as E by M ratio, 1.76 into 10 to the power 11 Coulomb kg inverse. Irrespective of the gases, we are getting this value. You take any gas, you will get the same value, because by changing the gas, we are not getting different things. We are getting electron as the cathode ray. And there was one more scientist, he calculated the charge on electron, Millikan. Millikan, by his oil drop experiment. By his oil drop experiment, he calculated the charge on the electron, which he found it as E. The charge on electron is, of course it will be negative, but I am talking about the magnitude. It will be negative 1.602 into 10 to the power minus 19 Coulomb. So after getting the charge and this E by M value, you can get the mass of electron also, mass of electron. So mass of electron will be, how we will calculate it? We will be dividing the charge by mass, E by M ratio. And we will be getting the value, if you calculate, it is 9.1 into 10 to the power minus 31 kg. That is the mass of electron. So very interesting thing, by having this cathode ray experiment, one more benefit we got is the mass of electron. So this was the cathode ray experiment carried out by J.J. Thomson. So definitely J.J. Thomson is responsible for the discovery of electron. So let us continue. The next discovery, that is the discovery of anode rays. See, in 1859 we had the cathode ray experiment, and in 1886 we had the anode ray experiment, which was carried out by Goldstein. Similar representation. The only difference is that we are having this perforated cathode over here. Perforated means we are having holes in this cathode. So everyone must be having this doubt, why we need a perforated cathode? See, penetrating power. If you see penetrating power, the penetrating power is directly proportional to velocity and inversely proportional to mass of the particle. So this anode rays, they are having higher mass, so they are having low penetrating power. So they cannot penetrate from this cathode easily. So we are having this perforated cathode. So important thing over here is the same thing is happening in this discharge tube. We are having, suppose, hydrogen gas. We will be getting 2H plus 2 electron. This time, this positively charged H plus, they are our anode rays. So you can see over here, if we are changing the gas, suppose instead of H2, if I take D2, what will happen? You will get 2D plus 2 electron. So we are having a change of anode ray. Now we are getting D plus as the anode rays. So it is a very important point over here that instead of H plus, now we are getting D plus. See, H plus, as you can see over here, H plus has only one proton in it. It was having electron, but due to the plus charge, we got ionized, and the hydrogen is having loss of one electron, and this H plus is having only one proton. So H plus is nothing but proton. So definitely Goldstein, first of all, he took the hydrogen gas, and during this hydrogen gas, we got this H plus as a proton. So proton discovery definitely took place when he took the gas as hydrogen gas. Because if you change the gas over here from H2 to D2, the anode rays are changing. Now you can get the deuterium plus, which is of course not the proton, because deuterium is having one proton and one neutron. So you are getting a very important point over here, that in cathode ray experiment, the E by M value, charge by mass ratio, did not change by changing the gas. But over here you can see that by changing the gas, there will be change in the value of E by M ratio. The E by M ratio value will be changing, because you can see the anode ray is getting change over here. Okay. So it is a very important question they are asking. The E by M ratio for anode rays. First option is varies with the element forming the anode in the discharge tube. No, beta, this is not possible. Second option, varies with the gas in the discharge tube. Definitely you saw over here, this thing took place. We saw this over here, that by changing the gas, there was a change in the value of E by M. So varies with the gas in the discharge tube. You can see now only we had proved this. Okay, that the E by M ratio value for anode rays changes with the change in the gas. Definitely why this took place? Because the anode ray is changing over here. It was H plus before, and then after changing the gas to D2, we get it as D plus. So it is a very interesting question over here. Let us move forward now. See, after a very long years, you can see that now in 1932, after so many years, it took place that the neutron discovery was not happening. Why? Why so many years? Because neutron is very difficult to discover. It is neutral in nature. But by very hard work, a scientist called James Chadwick, what he did? He discovered the neutron. He carried out a nuclear reaction over here. You can see beryllium Be49 was bombarded with a alpha particle. This is nothing but alpha particle. And you can see over here we are having nuclear reaction. We got carbon 12 and a particle called neutron. Why it was named neutron? Because it was neutral in nature. It was having mass approximately equal to the mass of proton, but it was neutral in nature, so it was named neutron. So the discovery of neutron was made by James Chadwick. So let us move forward now. Let us have the atomic models over here. As you can see, the first atomic model given was by J.J. Thomson. It is a very simple model. What he thought was like this atom is like a watermelon where the seeds will be acting as electron and the red part will be acting as proton. Or he called it as plum pudding model, where the plum in the pudding, the plum will be having significance like electron and the pudding will be having a significance of proton. So you can see, or it is a very simple model. He thought that electrons will be the seeds in a watermelon and positive charge will be the red part. So it was a very basic model. No one actually thought it is a correct model. And one scientist was there called Rutherford. He challenged this model, and by his famous alpha scattering experiment, he proved this model to be wrong. So let us see the famous Rutherford's alpha scattering experiment. So what did Rutherford do? He carried out the famous alpha scattering experiment. He bombarded alpha particles on thin gold foil. And what was the observations we are going to see over here? He had an alpha particle source over here, alpha particle source, and he bombarded alpha particles on the thin gold foil, and you can see what happened. In 20,000, one alpha particle got rebounded. See why this happened? Because alpha particle is nothing but helium plus 2 ion. It is a positive charge ion. And of course, this nucleus of atom will be having plus Ze charge over here, plus Ze. So like charges repel each other. Definitely, what will happen over here? See, suppose I am a helium plus 2 particle and there is a nucleus. Initially, I am having a velocity v. I will be going towards the nucleus of the gold foil, gold atom. But I will be getting deaccelerated. Okay? So same thing is happening over here. This alpha particle 1 in 20,000 is getting deaccelerated and it will be rebounded back. So what will be the observations that he saw? The observations were most of the alpha particles were passed undeflected. You can see over here. Most of the alpha particles pass undeflected. Some were deflected by angle. You can see some were deflected by angle theta. And 1 in 20,000 rebounded back. So 1 in 20,000 rebounded back. That means what is the conclusion? The conclusion is that most of the atom is empty space. And there lies a small region in the center of the nucleus where all the positive charge is concentrated. And thus Rutherford was the one who discovered the nucleus. So discovery of nucleus was done by Rutherford. And the final point, that the electrons are revolving around the nucleus in circular paths. These were the observation conclusion by the Rutherford. So these are the conclusions that Rutherford gave. And he also did an estimation of the distance of closest approach. See, dear students, let us understand this concept, distance of closest approach. So it is the application part. So this is our nucleus of gold and this is having charge plus Ze, where Z is the atomic number. And over here this is the alpha particle 1 in 20,000. I am talking about the one which got rebounded. It is having charge plus 2e. So what will happen, dear students? Let us see. See, this distance between the nucleus of the gold atom and this alpha particle. Initially, it will be a very long distance. So initially, the distance between these two is infinite. It is infinite. Okay, but what will happen as this alpha particle is moving towards the nucleus? It will get deaccelerated, as just like as you throw a stone over upside. What happened? It deaccelerates due to gravity, and the velocity go on decreasing, and after some time it comes down. Similarly, what will happen over here? Alpha particle initially it will be having potential energy K Q1 Q2 upon R, and the R value is infinite, so the potential energy initially will be equal to 0. It will be having kinetic energy initial equal to, what will be the kinetic energy? Let us take mass of it as m, and velocity is v alpha. So what will be the kinetic energy? Half m v alpha square. Okay, so this is the total energy initial we are having. But after some time, as it reaches over here, this is the distance of closest approach. It can be as small as the radius of the nucleus. This is radius of the nucleus, and we are having finally over here, finally beta, what will be the velocity over here? It will be, final velocity will be 0. Mass, of course, mass will be there. Mass is m. So what will be the final kinetic energy? Kinetic energy final will be equal to 0. But now we will be having the potential energy, because now we are at a distance of radius of nucleus. The potential energy final will be K Q1 Q2 upon R. That will be K into Q1 value, suppose it is plus 2e of the alpha particle, Q2 value plus ze divided by radius of the nucleus Rn. So this is our total energy final over here. So let us see the distance of closest approach by having conservation of energy. Conservation of energy. Total initial, all the total energies initial and final will be equal by the conservation of energy. So it will be kinetic energy initial plus potential energy initial equal to kinetic energy final plus potential energy final. So let us put the values over here. Kinetic energy initial is half m v alpha square plus potential energy initial is 0 is equal to, finally we are having kinetic energy 0 plus k 2k z e square upon radius of the nucleus. You can see this will be 2k z e square upon radius of the nucleus. So what we are getting over here, radius of the nucleus will be, this 2 will be multiplying over here, 4k z e square upon m alpha m v alpha square. So this is the radius of the nucleus, which is application part over here, that Rutherford was responsible for the calculation of the radius of the nucleus, because by having this experiment you can get to know of what order the radius of nucleus can be. So by this experiment only we came to know that radius of the nucleus is of the order of 10 to the power minus 10 meter, or you can say 10 to the power minus 8 centimeter. That is the radius of the nucleus. And radius of atom you can compare with that. The radius of atom will be having value 10 to the power minus 10. Of course, radius of atom will be of 10 to the power minus 10, and this will be 10 to the power minus 15, and this will be 10 to the power minus 13. This will be 10 to the power minus 15 meter, and this will be 10 to the power minus 13 centimeter. So radius of atom will be 10 to the power minus 10 meter, and by this experiment, the radius of nucleus, it was of the order 10 to the power minus 15 meter and 10 to the power minus 13 centimeter. So the questions they are asking over here, let us see what questions they are asking. So this question B, let us see what is the question. Find the distance of closest approach when an alpha particle is projected towards the nucleus of silver atom having a speed v. So of course now only we saw the radius of nucleus formula, that is 4k ze square upon m. They are taking as m alpha, so we are taking m alpha as the mass of alpha particle, and v square. And what is the z value? Silver having atomic number equal to 47, put the value 4 into 47 k e square upon m alpha v square. So radius of nucleus over here is how much? 4 into 47, it is 188 k e square upon m alpha v square. So this is the radius of nucleus we are getting. So of course B option will be our answer. Okay. So this is the application part question they are asking. Now let us continue. So as I said, the size of the nucleus was found, and as we discussed that the diameter or the radius order will be of 10 to the power minus 8 centimeter, and the radius that I saw over here, radius of atom will be 10 to the power minus 10 meter, and radius of the nucleus will be 10 to the power minus 15 meter. So it will be about radius of atom is 10 lakh times 10 lakh beta 1 lakh, sorry 1 lakh, and that will be 100. This is 1 lakh times more than nucleus. So the ratio, we can find out the ratio here, radius of atom upon radius of nucleus will be 10 to the power 5 times. Okay, 10 to the power 5 times. If they are asking us what will be the volume ratio, volume of the atom upon volume of the nucleus. So already we know the volume of the sphere, 4 by 3 pi r cube, 4 by 3 pi, and radius of atom cube upon 4 by 3 pi radius of nucleus cube. 4 by 3 pi cancel over here. So we are having 10 to the power minus 10 cube upon 10 to the power minus 15 cube. So what is the volume ratio over here? We are getting 10 to the power 15 as the ratio, 10 to the power 15. Okay. So these questions also they are asking. Now let us see the next concept, which is related to a formula, the radius of nucleus. They are asking radius of nucleus is equal to r naught a power 1 by 3. This is also a formula which tells us about the radius of the nucleus. Radius of nucleus is r naught a power 1 by 3. This formula, they are having a concept like nucleus will be having size according to the atomic number. So question they are asking over here is, which of the following element has the maximum density? They have given us the atoms over here, and they are asking us which of the following has maximum density. So I told you now, the radius of nucleus is equal to r naught a power 1 by 3, where a is the mass number. A is the mass number. So let us see what will be the answer of this question. See, density is equal to mass upon volume. Density is equal to mass upon volume. Everybody knows. And mass is nothing but mass number A divided by volume is beta, volume of a sphere is 4 by 3 pi into radius of nucleus cube. So as you put this value over here, A divided by 4 by 3 pi into radius of nucleus cube, you got over here r naught cube into a power 1 by 3 cube will be a. So a is getting cancelled over here. A is getting cancelled over here, and we are having all the density value will be equal. So density for all the density value is equal irrespective of the atom, whether it be silicon, phosphorus or oxygen, we will be having same density of the nucleus beta. So the answer will be all have the same density, all have the same density. Okay. So one more question we can have over here regarding this. Find the radius of nucleus of an atom having atomic mass number equal to 125. So here also the formula radius of nucleus is equal to R naught a power 1 by 3, and R naught value they are given 1.3 into 10 to the power minus 15 into a value is 125, 125 power 1 by 3. So we are getting 1.3 into 10 to the power minus 15, and 125 cube root is 5. So into 5, how much we are getting? 6.5 into 10 to the power minus 15. So B option will be our answer over here. So this is the radius of nucleus concept that we have gone through. That is the application part of the Rutherford's alpha scattering experiment. Okay. Light is getting incident on this metal plate. Like we will be having potassium, rubidium, cesium like metal plates over here, and this monochromatic light is incident on this metal plate. There is an ammeter over here which will tell us whether there is current flow or not, whether electron got ejected or not. The detector also tells us about this, whether the electron are ejected or not. So this photoelectric effect experiment was carried out, and this photoelectric experiment also proved that the electron has particle nature. So what was the observation during this photoelectric effect? See, a monochromatic light initially of very low frequency was incident on this metal plate, and what was seen? No electrons were ejected. There was no ammeter reading over here. The detector also said nothing. So when a very low energy or a very low frequency photon was incident on the metal plate, no electron was ejected. But then what they did? They increased the frequency, means the energy of the photon which was incident, and at a time when the frequency got equal to a particular frequency which we called as threshold frequency, what happened? The electrons were just ejected. They got ejected from the metal plate, and the detector detected them, and also ammeter reading shown some amperes current flow is there. So definitely this was the threshold frequency at which the photon was just ejected from the metal plate. When they increase the intensity over here, what is intensity? The number of photons which we are having incident on this metal plate, that is the intensity. Number of photons that are incident. When the intensity was increased, and suppose we are having the frequency of all these photons equal to threshold frequency, what was observed? It was observed that there was increase in the ammeter reading. That means more electrons were ejected. See, the photon just got incident, and within no matter time the electron was ejected. So this was a very important observation, that there was no time lag. As the photon got incident, the electron was ejected, and the intensity as it was increased, more electrons were ejected, provided that the frequency was equal to or more than the threshold frequency. If the frequency is less than the threshold frequency, what they saw? If we are increasing intensity over here, in such case no electron was ejected, no matter how much intensity you are increasing. So it is like a NEET exam over here, that in NEET exam we are having students getting prepared. If more number of students are getting prepared, see, it is not important that more number of students are getting prepared. It is our quality. If all the students have a preparation such that they are having at least that much capacity, that much knowledge, that much level of preparation, that they will be having marks at least equal to the cutoff marks, then they will go to the good medical college. It is like analogous over here. It is not about the number of students. It is about the quality. So same analogous concept you can have with the NEET preparation. And so the observations over here, as you can see, we discussed them, that there was no time lag. As the photon got incident, electron was ejected. And it was ejected only when the frequency was greater than equal to threshold frequency. One more point over here, that when the frequency was increased more, that it was having value more than the threshold frequency, what happened? This time the electron was ejected over here. It was ejected and it got accelerated towards the detector. Initially it was having some kinetic energy, and this kinetic energy initially we will have what this value will be. So see the difference of the energy that is required for the electron to get outside of this metal. See, every metal has some ionization energy. So of course we will be having some energy loss over here. We know that this threshold frequency, when it was incident, the electron was just ejected with kinetic energy equal to 0. So if we are having more frequency is more than the threshold frequency, what will happen? There will be some kinetic energy. The electron got ejected with some kinetic energy, and this extra energy, how much extra energy will be having? H nu minus H nu naught. This will be the difference and the extra energy which will be getting converted into kinetic energy, and we will be writing over it as kinetic energy maximum. Why kinetic energy maximum? Because beta, see, if this photon was incident on this metal plate, some loss of energy might be there because of some collision. So we cannot definitely say that the difference will be equal to the kinetic energy. There will be some loss of energy over here. That's why, because of the collisions, that's why we can say kinetic energy maximum will be equal to h nu minus h nu naught. Okay, that's why the formula is kinetic energy maximum is equal to h nu minus h nu naught. One more interesting thing that I want to tell you, suppose this is a metal plate, and suppose here is the electron and a photon gets incident over here. What can happen over here? If it is coming out, it might have so much collisions that in some cases, even if this threshold, if this frequency is more than or equal to threshold frequency, it might happen that this electron is unable to come out. Some cases it can happen. So you cannot say that if you are incidenting 2000 photons with energy which is more than this h nu naught, more than h nu naught, this is our work function, which we are calling it as work function. Over here I am denoting it as W. So this is the minimum energy that is required to photoelectric effect to take place. That is the work function h nu naught. And the minimum frequency we have to have the photon is threshold frequency. Threshold frequency over here. If we are having this photon with minimum this frequency or minimum this work function energy, it get ejected with kinetic energy 0, but not 100 times, not 100%. It can be ejected. You cannot 100% guarantee about it, because once they ask such type of question over here, we are having, let us see the question that they asked over here. A photon of energy h nu is absorbed by a free electron of a metal having work function W, which is W work function h nu naught is less than h nu. Means definitely we are having energy. This is our energy of the photon, and energy of the photon is more than h nu naught. So what do you think? Many of the students think that the electron is 100% going to be ejected out, but that is not the case. Just as I discussed over here, beta, what we discussed, that if a photon having energy h nu, where nu can be greater than equal to nu naught, it might be a case that this electron, if it is getting out, having some collisions, and for God's sake, if the collisions are so many that its complete energy is lost, it might get trapped inside. So you cannot say that always the photon having energy equal to or more than h nu naught, it will eject the electron. You can say it may eject the electron. So this question they ask, a photon of energy h nu is absorbed by a free electron of a metal having work function W less than h nu, then what will happen? First option is the electron is sure to come out. So this is the point I am telling you. You cannot say it will surely come out because of the collisions. You saw that. So this is a incorrect statement. The electron is sure to come out with the kinetic energy h nu minus W. See, two mistakes are there. First of all, it is not surely that it will come out, and also we will be having kinetic energy maximum, means you cannot say always it will be having h nu minus W. Because of the collision, the energy can be less than h nu minus h nu naught, where we are having this h nu naught as a work function. So this is also a complete wrong statement. Third statement, either the electron does not come out or it comes with the kinetic energy. What is this statement? Either come out or comes with kinetic energy. This is a completely wrong statement. And fourth statement, it may come out with a kinetic energy less than h nu minus W. So definitely this statement, as I discussed, makes a sense. You cannot 100% say that the electron will be always ejected because of this phenomena just I discussed over here, that there might be a case that the electron gets trapped because of the collisions. So you cannot say always it will be ejected. It may got ejected, and that's why this fourth option will be our correct answer. Okay. So over here we saw many important concepts, and the remaining concepts in this atomic structure is like Bohr model. In Bohr model, we saw that this Bohr studied over one electron species. The one electron species like hydrogen, helium plus 1, lithium plus 2, beryllium plus 3. Why he did all this? Because see, if we are having only one electron revolving around the nucleus, which is having plus Ze charge, which is having this plus Ze charge, it will be very easy to have the vectors over here, because there will be one force of attraction over here, because opposite charges attract each other. So force of attraction will be the centripetal force K Q1 Q2 upon R square, where we will be having K Q1 value as plus Ze, Q2 value as minus E upon radius R square. And one more force will be acting over here, that is the centrifugal force, which is force centrifugal mv square upon R, because this electron is revolving around the nucleus having mass m and velocity v. So the centrifugal force is also acting, and the centripetal force, that is the force of attraction, this is nothing but centripetal force acting over here. So we will be having very important Bohr model postulates over here. The first postulate said that as long as this electron remains in a static orbit, the total force acting on it will be equal to 0. So the total force acting on it equal to 0 means centripetal force plus centrifugal force equal to 0. Let us put the values. So what we will get, centripetal force is minus kz e square upon r square, and the centrifugal force is mv square by r. So the first equation we are getting over here is mv square by r is equal to k z e square upon r square. This is the Bohr's first postulate, where he said that as long as electron remains in a static orbit, the net force acting on it will be equal to 0. But only by having this first postulate we cannot calculate the radius value as well as the velocity value, because to equation we need two variables. So he further studied and gave another postulate over here, which was regarding the angular momentum. Bohr calculated the angular momentum of electron in various orbits, and he saw that this angular momentum is integral multiple of h by 2 pi. Just like in first orbit, he calculated it was h upon 2 pi. In second orbit, 2h upon 2 pi. In third orbit, 3h upon 2 pi. So he concluded that angular momentum mvr is equal to nh upon 2 pi. So this is the second equation. First equation is mv square by r is equal to kz square upon r square, and the second equation mvr is equal to nh upon 2 pi. Now we are having two equations, two variables, and you can calculate the radius and velocity value. So by having mathematics over here, calculating, we got the radius equation r is equal to n square h square upon 4 pi square mk z e square. That was the radius value. In this orbit number n is a variable and atomic number z is the variable. So all other values we can put over here, and we will be getting 0.529 n square by z angstrom, which approximately we can take it as 0.53 n square by z angstrom. So this is the radius which we can calculate of various orbits by having the Bohr model, of course for the single electron species only. And now we are putting this radius value in our equation mvr is equal to nh upon 2 pi. So by having this r value over here, we can get the velocity equation also. Velocity equation 2 pi k z e square upon nh. Now we can put the values of the 2 pi k. Pi is 3.14, k is 1 by 4 pi epsilon 9 into 10 to the power 9, and e value 1.60 to 10 to the power minus 19. Z is a variable, n is a variable. We will get the velocity equation 2.18 into 10 to the power 6 z by n meter per second. This is the velocity of electron in nth orbit. So by having radius and velocity, we can have different calculations. We can have the potential energy calculation, we can have the kinetic energy calculation, we can have the total energy calculation. So all these formulas are very important for us. So by having calculation, definitely you can go for the derivation. Kinetic energy is equal to half mv square. By putting the value of velocity over here and mass, that is mass of electron, as I told you, 9.1 into 10 to the power minus 31 kg, and the velocity now you saw 2.18 into 10 to the power 6 z by n meter per second. So by having these values put over here, we can get the value of kinetic energy. It will be 2.18 into 10 to the power minus 18 z square by n square. Of course it will be in joules over here, and by dividing it, divided by value of electron, E is equal to 1.60 to 10 to the power minus 19. You can get the kinetic energy in electron volt as well. It will be 13.6 into Z square by N square electron volt. So kinetic energy over here, we got it as kinetic energy is equal to 13.6 Z square by N square electron volt. Of course, before that we got the value 2.18 into 10 to the power minus 18 Z square by N square joules. Potential energy also we can calculate by having the formula potential energy is equal to K Q1 Q2 upon R. K, what is the Q1? That is the charge on the nucleus plus ZE. Q2 is minus E upon radius R. So potential energy we are getting over here is minus K ZE square upon R. So let us have the derivation over here. Look what here. What you can see. From here we can get one RR is getting cancelled. MV square is equal to KZE square upon R. If you multiply minus on both sides, you can see minus MV square we are getting. Minus KZE square is equal to minus MV square. We can use this over here. I can get what? Minus MV square. And definitely if you multiply it by 2 and divide by 2, we are getting half mv square into 2. And this half mv square is nothing but kinetic energy. So we are getting minus 2 times kinetic energy as the potential energy. As the potential energy over here. So we got the potential energy formula as well. Potential energy is minus 2 times, that is minus 2 into 13.6 Z square by N square electron volt, and also this minus 2 times minus 2 into 2.18 into 10 to the power minus 18 Z square by N square joules. So this is our potential energy. If you add both of them, we will get the total energy over here, and it will be minus 13.6 Z square by N square electron volt, or minus 2.18 into 10 to the power minus 18 Z square by N square joules. So there is a relation between these three, that kinetic energy is equal to potential energy upon minus 2 is equal to total energy upon total energy, and I am having over here only minus sign. Okay, so you can see this is the relation between kinetic energy, potential energy and total energy. Okay, you can remember it. You can get this from these three equations as you can see over here. So this is the Bohr model important formulas that you can see. There are many more formulas that you can have over here depending on which question they are asking. Now we are having one more concept, which is the dual nature of electron. Dual nature of electron by de Broglie. Here also important concept regarding de Broglie's hypothesis. He was the one who said that electron has particle nature as well as wave nature. And for this, he calculated the wavelength, de Broglie wavelength, lambda is equal to h upon mv, that is the de Broglie wavelength, in terms of mass m and velocity v, but we can have in terms of kinetic energy also h upon under root 2m ke. This is the de Broglie wavelength in terms of kinetic energy. Also, specially for electron, we can have especially for electron, in terms of angstrom, we can have this lambda value. Lambda is equal to 12.3 upon under root kinetic energy. Where this kinetic energy you have to put is in, kinetic energy will be in electron volt, and the wavelength we will be getting over here is in angstrom. This is a very important formula. Many questions are asked which you will have regarding this formula. This is a very important. Remember, this is only for electron. Okay. So in de Broglie hypothesis, we can have these important formulas. See, NEET exam, they are asking questions for the very basic formula we are having. They will not be going in very depth, where they are asking us many 2 or 3 combined concept questions. They are having simple formula based question over here. Okay. Yes, one question that you can have combined over here is lambda is equal to h upon mv. This is de Broglie wavelength, and one more equation, mvr is equal to nh upon 2 pi. This is our Bohr model second postulate equation. By having these equations together, they are asking a question, and let us see what equation we get by combining these two. So let us put the value of mv is equal to h upon lambda in this mvr is nh upon 2 pi. So what we are getting over here, h by lambda into r is equal to nh upon 2 pi. So we are getting 2 pi r. This h getting cancelled. 2 pi r is equal to n lambda. So this equation is very important. They are asking question related to this equation also. In NEET exam, they have asked this PYQs you can get on this equation, where they are simply asking us the wavelength lambda in a particular orbit. This 2 pi r represents the circumference. You know, mathematics, 2 pi r is the circumference for any circular orbit, 2 pi r. So they have asked question related to this 2 pi r is equal to L lambda. You can get, they are very easy questions. Just apply this equation, 2 pi r is equal to L lambda. Sometimes what they are taking this radius of first orbit of hydrogen, which we call it as Bohr's orbit. Bohr's orbit. They are taking it as A naught. So definitely they are nothing but they are having this A naught as 0.529 angstrom. So just we have to take the radius equation as r is equal to 0.529 n square by z. Instead of this 0.529 angstrom, we can put over here A naught. R is equal to A naught n square by z. Just use this equation over here. Put this equation in this 2 pi r is equal to L lambda. You are having 2 pi into A naught n square by z is equal to L lambda. So based on this question also they have asked, I think this is the same question they have asked in the PYQ, where just they are asking us third orbit, this third orbit circumference, and they are relating it with the wave number or wavelength. They are asking us wavelength. So just put over here the n value. This is the PYQ question they are asked. Put the n value, and they are asking us the wavelength of the electron in the third orbit. So what will be the wavelength? See, n getting cancelled over here. So value will be 2 pi into A naught, and n value is 3, and this is a hydrogen atom. I think they have taken hydrogen atom. For hydrogen, Z is equal to 1. So Z is equal to 1. So lambda we are getting over here is 6 pi a naught. So this was the question they are asked in PYQ. So this is a very important formula, 2 pi r is equal to L lambda, which we got by having these two formulas taken together. So this is another concept, that is de Broglie hypothesis, where he considered that electron shows dual nature, particle nature as well as wave nature. Next important concept we can have is the hydrogen spectrum. Just I told you that Bohr model, after Bohr model, we can have in-depth details where we will be talking about electron either getting de-excited or electron getting excited. It can be happening because if there is de-excitation, there will be emission of photon, emission spectrum, and if it is having a photon incident on the electron, that is absorption, you can say absorption. So we can have emission spectrum or absorption spectrum. Over here, the photon either get emitted or absorbed. So in hydrogen spectrum we are talking about this photon which is getting either emitted or absorbed, and we are plotting it on the wall, or you can say on a screen, and there we can see the spectral lines. Okay, we can have spectral lines. So they are asking us the value of spectral lines, that is the different energy lines we are getting, and simply remember the value of spectral lines, that can be maximum number of spectral lines. Maximum number of spectral lines that we can observe is delta n into delta n plus 1 divided by 2, where delta n is the difference, it is the difference between orbit number maximum and minimum. Means this is just like, suppose this is n2, this is n1. This is the orbit from where the electron got de-excited. This is the highest orbit number, this is the lowest orbit number. So we can have delta n over here. Delta n will be n2 minus n1. So we can calculate the number of maximum number of spectral lines. Delta n into delta n plus 1 divided by 2. Of course, these spectral lines will be having photons of different spectrums. They can be in UV region, they can be in IR region, they can be in visible region. Depending on that, we are having hydrogen spectrum divided into different regions. Lyman, Balmer, Paschen, Brackett, Peafold, Humphrey, they all gave different regions over here. In Lyman series, we are having only electron getting de-excited to the first ground state, and there we will get the UV region over here. In Balmer, we will be having electron getting de-excited to the second orbit. In that, the first 4 lines will be visible, and after that there will be infrared or UV, you can say, that will be having more energy. Only first 4 lines are invisible, that you have to remember. So there are different Lyman, Balmer, Paschen, Brackett and Humphrey. In the Lyman series, we will be having electron de-excited from any higher orbit. N2 will be like 2, 3, 4, dot, 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 infinity to the first orbit. In Balmer series, we will be having electron de-excited from N2 is equal to 3, 4, 5, dot, dot, from infinity to the second orbit. And all these three will be having, let us have one by one. In partition, we will be having electron getting de-excited from N2 is equal to 3, 4, up infinity to N1 is equal to 2. N1 is equal to 3. From 4, 5, from 4, 5, dot, dot, infinity up to 3. And in this, Balmer up to 2. Similarly, in bracket, we will be having electron getting de-excited from, this is N1. So in bracket, we will be having N2 is equal to 5, 6, infinity to N1 is equal to 4. In Humphrey series, we will be having electron de-excited from N2 is equal to 6, 7 up to infinity, from N2 6 or 7 or infinity to N1 is equal to 5. This Lyman series is in UV region. This Balmer in visible, just as said, first 4 lines will be invisible, and after that this partition bracket Humphrey, all will be in infrared region. Okay, infrared region. So I covered many of the important topics over here. Yeah, and there are many topics which we covered over here. Also question solving you can do. Most of the questions they are asking us is formula based in NEET examination, and just you saw many formulas over here. So definitely we can have questions on formula based questions they are asking nowadays, and in NEET examination we are having questions related to all these topics that you saw over here. Many questions they are asking in formula based. Further questions they are having like de Broglie hypothesis, we are having Heisenberg uncertainty principle. So in Heisenberg uncertainty principle they are having formula based on this equation, delta x delta p is greater than equal to h upon 4 pi. This is Heisenberg uncertainty principle, which relates that the delta x is error in position, delta p is error in momentum. So what is Heisenberg say that if you calculate the position as well as momentum of an electron at an instant, you will be having error in both calculation of position as well as error in momentum. And the equation over here will be delta x delta p is greater than equal to h upon 4 pi. See, this equation you have to use. They are asking us the value of delta x by giving the value of delta p, and while solving we have to take the equal to sign. Delta x will be equal to h upon 4 pi delta p. Suppose they have given us the value of delta p and we are calculating the value of delta x. Also this equation we can have in form of delta x delta v. Over here what will be having, delta p we will be putting it as m delta v. So as we put this delta p is equal to m delta v over here, we get the equation delta x delta v will be greater than equal to h upon 4 pi m. So this equation also you can use. They are having question over here where they are asking us suppose delta v value by giving the value of delta x. So while solving we have to take it as equal to, we will be having h upon 4 pi m delta x. So this is the equation which we can use over here. So this is Heisenberg uncertainty principle that they are asking. So all these concepts that we discuss over here, mainly questions in atomic structure they are asking us are formula based, and the tricky questions they are asking, I have covered them. So hopeful this was an important session about the atomic structure, and in today's lecture you got to know many important concepts, and also we saw the derivations regarding it. So let us meet in the next session, and today only we are having physics session for this power R, which will be given by the respected physics sir. So let us meet in the next session. Thank you for